I'm going to share my screen for them as well. Okay. Okay, we should be good now. Hello again, everyone. This is the task force meeting for the IEEE task force on digital twin of large-scale power systems for adoption of new emerging technologies. My name is Hossein Hooshyar, and I'm with New York Power Authority. I chair this task force. We're going to have a kind of Mission Impossible agenda for today for just 1 hour, but let's see how much we can go through. So we're going to do a very quick round table introduction. Then Ravindra will give us an introduction to the task force, the activities last year and the activities that we're planning for next year. There will be a presentation by our kind of sister working group on digital twin for power equipment by Professor Rick, who is the co-chair of this working group. I'm going to have Dr. Kaustav give us a short presentation about integrated measurement simulation approach for analysis of large power systems. And if we have time, I'm going to share with you some of the activities that we're doing in New York Power Authority for development of a comprehensive digital twin of the New York State grid. And then at the end, if there's any open discussion, anything to discuss, it's welcome. So with that, I would like to ask Ravindra to please give us an introduction. And if you can please hold this or just connect it somewhere. Otherwise the folks won't be able to hear you.
Yeah, hello everyone. My name is Ravindra Singh. I am a senior principal of distribution automation at National Rural Electric Cooperative Association. And I am the co-chair of this task force. My main area of research is distribution automation, renewable integration, microgrids, and cybersecurity of the power system. So do you want me to go ahead this presentation or do you want to have a round table?
Oh,
that's what
I missed it. So let's do a quick roundtable introduction. Just in the stress about time, I missed it. So let's go with just name, title, and affiliation. I think I introduced myself as Singh, Director, New York Power Authority.
Ravindra Singh, Senior Principal at NRECA.
So sorry, NRECA.
Terry Silva, Power Systems Trainer at California ISO.
Rob Podmore from Incremental Systems.
PhD candidates from Florida to North Carolina. Julia Morgan, I'm a Nova-based design researcher at International.
I was born from Systems.
Don Heider, cybersecurity research engineer at Prospect North Lab.
Ali Kassemian, Department of Energy, Office of Electricity. I'm a program manager.
Siwajo, Professor at Hong Kong College of Engineering.
Yes, Muhammad, Professor at University of Harvard University.
There is Associate Professor at Aarhus University, Denmark.
It is like from electronics in Austria.
I'm here at University of Leeds.
Professor at University of South.
Finish this row and then we'll do that.
So much Associate Professor at the University. Postdoc postdoctoral fellow at University of Manitoba, Canada.
Kinder Papa, PhD student at Michigan State.
This research fellow at the University of Maryland.
Java system facility center.
Is the army assistant professor from the college?
Yeah, from the University of California.
Stratis, assistant professor, University of Southampton.
Myself, Viyash, I'm a principal researcher at National Renewable Energy Lab.
Young student with the University.
He's now associate professor in the University of California.
So actually, postdoc at NASA almost.
PhD student.
Deepak, assistant professor in Ministry of Economic Affairs. As a CS, consulting agent. And PhD came from the University. Professor of Houston.
Thank you. Anybody want to join us briefly? This minute. Okay, thank you, everyone. Ravindra. Okay.
Yeah, thank you, Hossein. So as Hossein said, I will be providing a brief introduction of this task force, what we have been asked, and what's our future plan. So uh, this is the structure of this task force. So basically, this task force is sponsored by Technologies and Innovation Subcommittee, which falls under Power System Operation Planning and Economics Committee under PES. So Hooshyar, he's the chair of this task force. Myself, I am the co-chair, and then we have Malik. He's the secretary of this task force, and Rahul Kanavel, he is the webmaster. So next slide.
Have the microphone a little bit.
Okay, yeah, sure. So we started this task force last year, and our inaugural meeting was held during IEEE PS General Meeting in 2023. So the whole idea behind this task force was basically to create a community where we could have different stakeholders sharing their experience and concept of the digital twin related to the power system. Then another objective was to review the what's there, what are the state of the art technologies related to digital twin, and investigate the practical requirements, challenges and solutions in implementing the digital twin. And then finally propose a generic vendor agnostic high level architecture interface and technologies that support the implementation of digital twin. And finally, create examples and use cases based on the implementation and demonstration of this technology. So this is our web page. You can find more information about the task force on this page. Next slide. So this is a general description of different representation of digital twin. Our focus has been more on to system side, which talks about the comprehensive and transformative digital twin. Here is the definition. So digital twin is basically a virtual representation of an object or system that spans its life cycle, is updated from real-time data and uses simulations, machine learning, and reasoning to help decision making. And these are different use case scenario that we are trying to consider within the scope of this task force. Next slide. So as I mentioned, like we are not focusing on individual component, rather than we are looking into the holistic system and the system as a whole as a part of this task force. These are some of the activities. We have significant participation into this task force. We have vendors, research organization, energy utilities, education and training organization, and consulting services as the members. So we have a significant participation from people of diverse background. Next slide. And as a part of task force, we have bi-monthly calls where we invite different stakeholders to talk about and share their experiences related to implementation of digital twin technologies. So far, we have 7 seminars as a part of this task force. And uh, as we go forward, we will continue to invite speakers from different backgrounds to support us. So as I said, we have a web page. So if you go on our page, there is a resource section, and you can find all the presentation slides and details on our website. And next slide. So going forward, as I said, like we continue to engage with the stakeholders to share their experience. So as a part of our bi-monthly call, we will continue to do our regular seminars. So if you have any interest, you reach out to the officers to schedule for the seminar. And we are also going to start drafting the report. So if you have any interest in contributing to the report, please reach out to the officers. And going forward, we are also planning to propose a panel session. So if you have any interest in this panel session, you can reach out to us. So that's all I have for today. So I hand over to Hossein.
Thank you, Ravindra. Appreciate it. Yeah, so as Ravindra mentioned, this year, I mean, the first year was like more introduction to this topic and getting some information about different perspectives, how people from different sectors in the industry or academia look into the digital twin, especially in the context of large power systems. But this year, it's going to be more serious. And it's going to be organizing a panel session and creating a white paper, for example. So if you're interested in contributing, we welcome you very much. So the next part, the next presentation is from Professor Rick, who is a professor at Wuhan University and also the co-chair of the IEEE Working Group on Digital Twins for Power Equipment. So I think the title clearly mentions how is it different from what we are doing here. And also organization-wise, we are under PSOP, while Professor Rick's working group is under Transmission and Distribution Committee. They are a few steps ahead of us. They have published a white paper a few months ago, and I shared the link with everybody on one of these monthly calls. So I thought it would be a great opportunity if Professor Rick can share his experience with us about digital twins of power equipment. So thank you for coming, Professor Rick, and the floor is yours.
Which one to play?
Well, this is just a microphone. You just tell me, and then I'm going to
Okay.
go forward with your presentation. Just for the microphone so folks on the call can hear us, can hear you. Now let me see if I can go full screen. If there's any. I don't see any full screen
Page
option.
by page. Okay.
Well, there's no, okay. Back to the menu. You see full screen, okay.
Okay. Good morning, everyone. My name is Rick Shizhudong from Wuhan University. Actually, I work in asset management for a long time, from Progress Energy in Florida and to China Southern Power Grid. Now I'm in Wuhan University. And in last 2 years, as Hossein just mentioned, we set up a working group of digital twin for power equipment, and a white paper was published earlier this year. So I'm trying to use this session, thanks for Hossein's support, to share some progress, maybe can give y'all a kind of idea what's going on in equipment level. So next page, go next. Next, yeah.
Yes,
Next.
This is the second page.
Oh, second, go next. Now, what we are define, that's what our definition, similar what he just mentioned, that's a digital representation of a specific physical identity or process with online or offline data interaction, which ensure the identical behavior of a virtual entity to the physical ones at their life cycle management. So we basically wanted to have a transparent asset. So when we talk about the power equipment, we are focused on source, grid, load, and storage. So like the generator, transformer, circuit breaker, GIS, lens, all such kind of things. Next. So the way it's talking about digital representation, internet connection for all kinds of data, as well as the digital twin applications in our asset management level. Go next. Since there are a lot of slides, I'm trying to do quickly. Here's the one that basically everyone knows that a digital twin goes up about 20 years. So it is now it's getting harder in different industry. Go next. Especially in power industry. Now we are working in a kind of different level, like the physical identity, virtual identity, and how can we connect the physical and the virtual identities, and also the data and the services. Go next. The way I thinking is that we also go through the digital twin applications or and deal work in power industry. Now, basically in system level, they're using for grid dispatching and operation support, and also for the equipment level for asset management, like the transmission lines. And here is we basically figure out from the source, grid, load, and storage, what kind of equipment will be covered in our scope. Go next. The first priority is we need to identify what's the purpose of digital twin for the power equipment. So we basically figure out 5 purposes. One is to improve the quality and the efficiency of power equipment design and manufacture, and then to ensure the operational reliability as well as the health management. And also, it's easy for us to intelligent decision making to support maintenance, and also to coordinate the operation between source and the load, and also the storage. Later on, also can reduce the cost of employee training, and also make friendly marketing in supply chain. When I was at the utility, normally some salesman go to my office, try to introduce their products. It's sometimes takes some time. If you have a digital twin, you can use a very quick picture to show me what's your good stuff. Go next. Here is the structure we developed for the power equipment, basically including 5 levels. The physical level, that's all our physical identities. And the sensing level, basically we get the data from the field, like the online monitoring or offline data or operation data, and also the data layer, including the data access, connection, process, cleaning, or fusion or such kind of at the multiple spatial and temporal scale. And then given all that data, then we can develop the twin layer for the different identities. Given the twin layer, then we can go to the application layer, either for the supply chain department, or go to the maintenance department, or go to asset management department. That's the purpose. Go next. Yeah. So given that, we also try to summarize what kind of tools we are going to use at a different level. So here we try to see the physical model, geometry model, behavior model, rule model, and what kind of tools across the world. So we give a kind of summary for the different purpose. For example, like ANSYS or Simulink, all that used for the 3D multi-physical field analysis, and for the such kind of automation, machine learning is used for the rule model. So that's a kind of tools summarized. And also for each layer, we also shared that what kind of techniques we need to use for this layer. For example, like physical and science layer, you need to think about the maps. So we are developing some nano or micro sensors to connect electrical data like current, voltage. We also use to connect other information. So we need to develop the maps for the equipment. At the same, go back. Yeah. So also we need to use Internet of Things to connect all that data from different time scale. And at the data level, then you need to think about the data process and the privacy and cybersecurity issues. For twin layer, that's a key issue. You need to think about a multi-physical simulation of power equipment. Just if you do ANSYS simulation for bigger transformers, normally it takes about 10 to 20 hours for a simulation for the electrical magnetic field analysis. Now we need to find a way for the faster simulation. That's one of key issues. And also for the edge cloud collaborative computing and also the AI stuff will be used in twin layer. So develop a kind of mechanism and the data-driven models. How can we put it together? And for the application level, then we need to think about the HMI, the interface. How can we make that happen? So that's a bunch of over 20 techniques we identified to support the different layers. Yeah, go next. So here's some key technologies at each layer. So I do not need, since the time I will not repeat. Go ahead. Go. Next. Yeah. So given that we worked at a working group over 20 companies and over 70 researchers, engineers, and developers together, we come up all kinds of digital twin models using different tools. For example, like this one, when we develop the equipment models, we need to think about the digital twin model, the mechanism model, the data-driven model, the hybrid-driven model, as well as the virtual 3D models. So for the load grid side, the power source side, and the energy storage side, all kinds of equipment, we are going to connect their use cases. Just give here's some examples. This one is a gas insulated line, that's a GIL. Here's the wind turbines and also the transmission lines. Go next. Here, just give you example like the wind turbines that the Zhejiang University and also the North China Electric Power Universities, they develop a digital twin for wind turbines for the maintenance and the fault diagnosis. And for the inverters, Wuhan University and Nanjing, they also develop some digital twin for the power inverters, either for the different application. And go next. And also for transformers, that's a key component for our industry. So several utilities shared their use cases. Like this one, that's done by the Wuhan University and the State Grid, and also the circuit breaker underground. And also one interesting thing is from Hubei province. They also use a digital twin to develop the microgrids and also distribution stations, transmission stations, and also the system control room. Go next. And here's the pumped storage and battery energy storage units. Basically, they're all similar process, but they use different twins. Here's the load side, especially for electrical charging posts and stations. In China, now the electrical vehicles exceeded over 24 million. So they need a lot of charging stations. So that's why we need to develop a digital twin for the maintenance of that. So when we develop all that digital twin equipment, how can we use that? That's one of the issues. So we basically think about either use for manufacturing and design, or use for asset management in utility, or either use for end users. So we go next. So we basically talked with different companies, basically from generation company, the industry company, and also the power grid companies. We connected about over 11 use cases and how to share how can we use for different purpose. Go next. Here is the one that used for the mining company. They just develop a two 660 megawatt supercritical coal-fired unit. They basically, when they design and develop this power plant, they use digital twin from the beginning to the end, to the commissioning. So here's the way that for data connection to service layer to application layer, when you try to develop at this stage, what kind of material you need to prepare in the field, then it will automatically share in the virtual area. Go next. The state grid used digital twin for the supply chain. So that's one of platform they developed. So they are currently enrich this supply chain platform. The idea is that later on in the near future, when a utility will purchase a transformer, they are not only to purchase a physical transformer, at the same time, they will require the supplier to give a digital twin entity. So we will share this for the physical transformer will be put into the on-site. At the same time, the digital twin of that transformer will put into the asset management tool or either to the operation purpose. So that's a kind of two parallel way for the supply chain later on. Here is the one developed by China Southern Power Grid. They use a digital twin to develop a cylinder stress of a GIS section at a 220 kV substations, so they can easily to identify to connect the partial discharge or the hot spot or temperature stuff inside of that section for the fault diagnosis. Go next. Here is one from Zhejiang Utility. they use the digital twin for the transformer maintenance and asset management. So they integrated the multi-physical analysis at the different operation conditions. So given that level of loading, what's the temperature field inside of that big transformer? What's the hot spot temperature? Then they can see the dynamic rating of that transformers. So for all that condition assessment purpose. Go next. Actually, that's another one from China's China IEEE. They use the digital twin to develop a kind of virtual routine check platform. So they coming up all kinds of data when they do the routine check of substations. So you can connect the visual information, the infrared temperature information, and also partial discharge information, also the online gas in oil information. So you go next. Here is actually a kind of animation. I cannot show up. So you can just like a bird view from the broader substation. Then you can see the temperature distribution. Then you can go deep into the transformer. Then you can see the temperature distribution across that transformer. Then you can go into the transformer. You can see the hot spot of the transformer. So that's the kind of way we are doing. And also for power plants, for the nuclear power plants, we all have that cases. Go next. And also for the converters. Yeah, so next. Yeah, okay, go. Let's go. So basically, that's all information we try to share. Go next. At the same time, we are trying to develop a series of standards, try to standardize the process. How can we use the digital twin for each equipment, and how can we develop such kind of standard language? Go next. Go. So last page is that we basically given the work we learn a lot, and basically there's some challenges we need to think about. One is that what kind of technical challenge, like the data standardization, also what kind of tools of digital twins. Everyone said that they develop a digital twin, but they cannot communicate together. So that's why we try to standardize the developing tools and also models, platform, and others. And so go next. So basically, that's the work of our working group, and it was set up, kick off at 2022. And me and Dan Sabin from Schneider, we co-chair that. We currently have over 70 active members are developing the different use cases. So, okay. Yeah. Thanks a lot. Yeah.
Maybe we can take one question. If there's any question. One question. Maybe you guys can take it offline. Thank you very much.
Thank you.
If I can have the microphone.
Thank you.
Have the microphone.
Oh, Michael.
Appreciate it. Thank you. So our next presenter is going to be Dr. Day. Going to pull up his slides. Okay. Thank you. Thank you.
So is it audible? It's not a good idea. Yeah. Yeah. So, hello everyone. I'm Kaustav and I'm a postdoctoral fellow at University of Manitoba. The work that I'm going to present here is based on an actual blackout event in India, and the study we had done was part of my when I was doing my PhD in India. So this is an actual study, and the idea will be reflected how digital twins can be used to do post disturbance analysis to recreate the situations under disturbances. So before we start, I will give you a brief description of the system so it builds a motivation what exactly we are studying. So this is the Indian grid, and the India country, as a big country, we have a one single grid for the entire nation. That means there is any part to any part of the country is connected by a synchronous connection. And in the broad sense, the country is divided into 5 major regions consisting of several provinces, and the major regions are connected via interconnecting lines, which creates the grid structure. And in specific, the western region, there is a state Maharashtra, and Mumbai is one of the big cities and big load center in India. So what happened on 12th October 2020 is that this is the big picture of Mumbai, that in Mumbai there are mostly two big generating companies, Tata Power and Adani, and the Mumbai loading is significantly higher than the generation capability. So normally the power is being imported in Mumbai, and due at the instant of the disturbance, the amount of power that was being imported was around 2 gigawatts. So there are a couple of 400 kV double circuit AC lines and several 220 kV AC lines that give the power to the Mumbai city. As you can see, they are colored red. Some of them are colored in a shaded manner. Some of them were out for some scheduled outages, the maintenance. So what happened is that the system was heavily loaded and a couple of transmission lines were out for maintenance. And due to some disturbance or due to some trippings in the protection circuit, the 400 kV line, which was carrying a huge amount of power at that point, suddenly tripped, and that causes an unscheduled or an unintended islanding of the Mumbai system. And the Mumbai system had such a big generation load imbalance that it suddenly went into the frequency started to collapse, and each of the generating companies had their own islanding schemes. But as you know, in most islanding schemes, they work on the rate of change of frequency, and there are some intended delays to avoid unintentional islanding. So among the Tata and the Adani islands, the Adani island somehow could survive because of their settings, whereas the Tata island failed to survive on its own. Before the islanding scheme completely activated the generator under frequency relay strip because of the high frequency rate of change of frequency, and it went into a complete blackout for that Mumbai city for some time. So the study we had done was Tata wanted us to do a study and check what could have been better settings and how this issue could have been prevented. So our objective was to study the Tata Power part of the system, and we were given the generator substation disturbance records, the voltages and currents being measured by the disturbance records, and we had to check what are the possible schemes in which this could have been avoided. So in a nutshell, this is the kind of system it had, that there were two main generating units in the plant, and they are called being unit 7A and 7B. So 7A is a gas turbine plant, and the waste heat of the 7A is being used as the prime mover of 7B. So 7B is kind of a steam turbine plant which relies on the waste heat of 7A to operate. And the sequence of event is 7A got isolated due to under frequency relay, as you can see, but 7B continued to work being connected to the grid. So 7B, although the 7A got tripped and its prime mover also got tripped for 7B, it still tried to supply the power from its rotational kinetic energy as long as it could. And what is the problem that we are trying to estimate? Okay, when we are given the disturbance records, we know that we want to make a simulation model of the system. It's a steam turbine based generator. And in order for the simulation, before we can confirm anything, we need to ensure that we are able to recreate the same scenario in the simulation structure. So we needed to ensure that the same voltage and current profiles we could emulate in our simulation model. As you know that in a synchronous machine or in other kind of systems as well, there are a lot of inputs that come into the system that has to be input properly. For a synchronous machine, it is the prime mover which is being controlled by the governor, or the field voltage which is being controlled by the excitation system. So unless we have the correct patterns for these components as well, it's very hard to replicate. So this is one of the possible challenges when doing a offline simulation, that due to black box controllers or not knowing the intricate details of the controllers always, because although we sometimes have a fairly well detailed linear model of the controller, sometimes the non-linearities like dead bands, limiters that are usually present, but they are normally inactive. They are activated only under extreme situations. We may not always have the data very accurately for these components. And under such very rarely observed scenarios, it is very important to know the entire details in order to do an accurate modeling and reconstruct the scenario in our simulation. So what we try to do here is to go into an alternative approach rather than doing trial and error to fit a certain model of the governor with a certain set of parameters and trying to fiddle around with a trial and error manner. We went into an integrated measurement simulation approach. So the idea is, I have a certain set of disturbance record measurements. Suppose it could be the terminal voltages for a synchronous machine. And the synchronous machine I am using from in my simulation model, I assume that the control variables like the mechanical power, field voltage waveforms are not known to me. And I start with an initial guess. I try to see, okay, what are the things I want to match? So I should try to match, say, the active and reactive power going out of the machine. So it is like an optimization problem where we check the error of our measured variables, that, okay, I have a set of P and Q which are being given by the DR measurements. And I try to see, okay, what are the P and Q waveforms I'm getting in my simulation? So I see an error, and automatically based on this error, I try to correct the mechanical power and the field voltage measurements waveform such that eventually I converge towards that case, because until we reconstruct that exact scenario, we cannot draw inferences from our simulations. So in this manner, we iteratively update the unknown waveforms, and based on that, the schematic is something like this, that there is we keep a certain, the optimization window is set in such a way that we have a certain pre-disturbance waveform, so that we know our starting points to begin with. Before disturbance, we know the equilibrium points where the system was operating. And within the system, so ideally one would say, okay, in a simulation, what if I try to optimize the value of the waveforms at an arbitrarily close resolution? So the more number of dots you can see in that waveform, that those are the instants where we assume that the waveform can be changing, and we want to optimize that waveform to match the outputs. So the more points I try to put in there, the more number of optimization variables, and in other words, it's the more complex task. So the choice of how much densely we want to put the unknown variables is up to us. Sometimes we may not have an idea. For example, if it's a static field exciter, we know it has a high bandwidth and can change very fast. However, we can do some constraints based on our physics of the system, such as if we are optimizing the prime mover input. We know that, for example, a reheat type of system, a governor is very slow. It has associated with large mechanical time constants. So we can assume that these points can be quite far from each other. There will be no faster variations in very short duration. So using these physics informations, we can try to reduce the optimization problem we have in our hand. This is more of a practical challenge rather than a theoretical challenge. Ideally, given infinite time, we should be able to iterate it. But often these are big tasks to be done. And these are, so as I said, that the resolution and the optimization, the complexity of the optimization problem is a kind of trade-off that one has to select. So based on this idea, what did we see? So in our simulation model, these are the frequency and voltage waveforms that we saw from the DR measurements. The active and the reactive power, as you can see, had wild fluctuations in them during the disturbance. So we wanted to match these waveforms. What waveforms of mechanical power gives us this type of active and reactive power for that generator model? And so the prime mover we were trying to optimize, and the measured variable was we are trying to match the active power based on this. So we started off with an initial guess, and gradually, due to keep the discussion brevity, I did not put all the initial waveforms. But since I have already given you the description that the turbine input is coming from the waste heat from another generator. We understand that after that generator tripped, its waste heat supply will also be stopping after some time. So we assume that the prime mover input to this generator will be reduced after a time. So we were trying to optimize that delay. That you can see the black waveform is the mechanical power we were trying to optimize. So we were trying to find out, okay, after the first unit has tripped, how much time after that the mechanical power goes away, because we know from the physics of the combined cycle plants that this is how the mechanical power will eventually change. So based on that, we were trying to fiddle around that delay tau, and we eventually found that a certain value of tau as shown in the waveform, which is close to about something less than 1 second, gives us a very good match in the active power. You can see the red one is the measured active power, and the blue one is the active power, that waveform that we got in our co-simulation model. So you can see there is a fairly good agreement between, and we can say with confidence that we are able to set up the same operating condition as the system was facing. And so after this, we can carry out all the inferences to be drawn that what could have been done to improve the islanding schemes and such things. Yeah. So these are the same things that I told. And a similar observation in one of the other units, we were trying to optimize this is another steam turbine plant, and we had the same issues. We have the terminal voltage and frequency measurements, and we wanted to match how the prime mover variation you can see. And in short, I will tell you the figure on the bottom. This figure, if you can see the cursor of the mouse, this is the figure where you can see that after optimization, we found that the mechanical power decreases with a certain time constant, which is as expected because there is certain time constant with how governors work. So, but we did not have the detailed models of the parameters. So we were able to get back some kind of idea about how these controllers inside the system are working. So this does give us some indirect knowledge about the missing information in our models. And to conclude and put the future work in perspective are that real life outages, this is always required for system operators when they do the study after any outage, that what had caused the system, the root cause analysis, how to do preventive measures and improve the system to avoid such further incidents. And we typically always have good resolution disturbance records at most of the critical units, and therefore getting the data and for these simulation setups is not a big challenge. But the main issue that in further times when we are replacing synchronous machines with more and more inverters, we know that even with inverters, the issue of black box control is even more. There is even lesser transparency to that models, especially that when the nonlinearity is needed to be carried out. So rather than, this is an alternative approach in which rather than trying to guess and fit a certain model to ensure that the waveforms fit, we replace the unknown part of it and try to optimize the output of those controllers and then back calculate what should have been the controller structure based on that information. And some of the future works right now that we are thinking, and we can open the questions for anyone if you are interested, is that what if we can check out how different optimization tools, what we know certain optimization algorithms work very well for certain type of problems. So given this type of analysis, what would be a reasonably good, what such comparisons will be really helpful. Identify certain interesting input output variables if we can generalize, for example, when we are trying to match active power, whether the prime mover is an important piece of information or not, and how to incorporate the bandwidth constraints. For example, we know the prime mover of a large machine cannot change very fast. So how this type of informations can be mathematically put as constraints into this optimization problem. So generalizing this problem and trying to develop a more unified structure would always help to solve this problem at better ease. And to acknowledge these are some of the people who were very much involved in this work and helped us to develop this part of the work. And if you want to study on the further details of this incident and the reports and the observations, these are two of the key references, the incident details and the key observations of the post analysis studies are reported in details in both of these papers. So if you have any questions.
Thank you, Kaustav. I appreciate it. Any question for Kaustav? Maybe one question, please.
doing the simulations, they have the model there. So how this is related to the previous pin in terms of the 16 simulation?
It is not for always for maintenance operation level, but this is when you are trying to recreate very large disturbances. Sometimes we do not have complete details of the controller models and everything. We sometimes have a limited information model which works very accurately under normal situations. But when you have large system deviations, say frequency falling down at a very fast rate, a lot of rate limiters and other components get activated, which may not always be available to us. So we found that some of the simulation models we had for some of these components were not able to replicate some of the waveforms we were seeing from the DRs. So that's why we kind of tried trial and error to go back and eventually found that this may be an easier way rather than to fiddle around with an incomplete model. So that was our observation.
Is it okay if we continue that offline? Because I know folks want to go for lunch and we need to wrap up soon. Is that okay? I'm sorry. Thank you.
Thank you.
Appreciate it, Kaustav. You can please. So I do a very quick intro to what we're doing in NIPA, and then hopefully we will have to. I can find my mouse. Okay. All right. So that will be a quick presentation. Basically, New York Power Authority, as many of you might know, is a transmission owner as well as a generation owner. And here, my point is not to introduce NIPA, but I think what matters is that why a utility like NIPA should care about digital twin and creating a digital twin. NIPA is also part of the state government, so it matters to NIPA that, okay, how far we're making progress in with respect to all of the goals that we have with respect to renewable energy resources. And NIPA recognizes that this will impact all of the utilities, including NIPA. So it will impact the system operation, which might be something that New York ISO would care more about, but also the assets as well. And since NIPA is an asset owner, it matters to NIPA. So in order to basically analyze the problems that we might be anticipating in the future and also finding solutions, NIPA created this facility called Advanced Grid Innovation Lab for Energy. And this is where we're creating the digital twin of the New York State grid. It's not just the territory of NIPA, but for the full grid, basically everything that New York ISO operates. And in terms of use case, this is basically a copy paste of what Ravindra presented. Basically, we're looking pretty much into everything that one can think of as a use case of a digital twin. Realistic testing, control room advisory. So the plan is basically to take this digital twin, make it so mature that it can be taken into the control room. Predictive operations, education and training, and et cetera, et cetera. So this presentation is about a conceptual design of the digital twin that we have envisioned. This is not about implementation. That requires another presentation, hopefully in the panel that we're going to get approved for next year general meeting. A couple of considerations before we started this conceptual design was that in the concept of power grids, it's not only the power grid, but also there are other systems that interact very actively with the power grid. So the question was that in the digital twin that we want to create, what piece we should include and what piece we should just have it outside and do the data exchange with it. And obviously there are many different systems interacting with the power grid, but since ICT, the communication network in the substation, between the substations and the control rooms, and from the control rooms to New York ISO, plays a very key role, very integrated role in power system operation, we decided to include that in the digital twin of the power grid. And the rest of the systems will be developed later as a model, as a digital twin, and will exchange data with the digital twin that we're envisioning. So it will not be part of the implementation. And also, we knew that, creating a digital twin at this scale will probably take decades to be completed. So we cannot have all of these small pieces ready and then we stitch them together and make it a digital twin. That is not possible. So the mentality that according which we started this design was that we have to create the capacities and then we let them grow over time. So for example, if you want to include a distribution network, which might be millions of nodes, we will create that capacity, we will create that interface that connects the digital, the distribution part of the digital twin with the transmission and the rest of the network, but we will let it grow as time passes. So we'll start with the baby digital twin and we will grow the capacity. So just to give you an idea of what our digital twin look like, because digital twin is a word can be interpreted in 100 different ways. I'm going to show you the dissection of the digital twin in 3 levels. So the first level, which is the top level, is the digital twin, is the black box digital twin that, as I mentioned, will interchange some measurements or data or some sort of information with the rest of the systems. So for example, it requires the real-time data. This might be the data that we can bring from our control room, the breaker status, load levels, dispatch of the generations, as well as weather data. It can interface with the digital twin or models of other energy systems if we have any. I just remembered that I have animations for it. And also with the component level digital twin. So for example, in NRECA, we have a center called ISAC that basically monitors very carefully those important assets of NRECA. For example, not all of the transformers, but a few transformers that are of very much of importance. So that connection can be made. Also, the interface that like the traditional hardware in the loop, power hardware in the loop that can interface the actual equipment with the digital twin, as well as interfaces for absorbing DLL and FMUs. Now, if we go 1 level down, so this is going to be level 1, this section. On the left side, basically, these are all the inputs and outputs to the digital twin that I've already mentioned. But that this digital twin will have an offline database that will basically have all the information that we receive in real time, but for the recorded for the past time as recorded data, and also forecasted data for future time. And it's going to have a controller that is basically a user interface that the operator of the digital twin can interact with the digital twins. For example, it can set the time, hey, become live from this hour, this day, and this year. So the digital twin becomes live from that time. The user can do data logging as well as event playback and some other components. There will be another component, which is basically 2 things lumped into one feature, is basically having wall monitors or virtual reality-based perspective or 3D immersive visualization for the sake of analysis as well as education. And also a copy of the SCADA and EMS system that we have in our control room, the actual ones, in the connected digital twin, and it will work the same way as it works with the actual network. So we will be able to see the same thing as the operators see, with the difference that they're looking at the actual grid, we're looking at the digital twin of the grid. And the main part is, now we go 1 level down again, is basically a repository of all of the models that we want to create for different sections of the grid. So it's going to have, so it's going to have different models with different resolutions for different years for the transmission. And the idea is that we have all of these different models for different resolutions vertically synchronized, meaning that if one change happens in one of them, that will be translated into the other platforms. Now here, the idea is not to promote different platforms. Actually, ideally, we would like to have one platform that serves engineers of different disciplines. No matter you're a planner, an operator, an outage scheduler, a protection engineer, you should be able to use the same platform. But because currently that's not the case, we need to make them vertically synchronized and possibly minimize as many as possible. Same thing with the distribution grid. Same thing with the communication network. We want to have a market emulation as well for different years. And also